All right, so now it's time for our eighth and final chapter of this book and this course. We're going to be looking at some more advanced techniques for calculating integrals. And I've said this a couple of times, integration is a very complex process. I certainly think it's more involved than derivatives, where there's not that many different rules available to us. But with integration, there's quite a few because there's so many different situations we could potentially run into. So we're going to look at four of the more important ones. And so they're called integration by parts, trig integrals, trigonometric substitution, and partial fractions. Okay, so each one of these is going to be useful under different circumstances. And like I've said before, the big challenge here really is recognizing when to use each of these techniques. Okay, so let's start with integration by parts. Now, integration by parts comes about from the idea that you have a function which is itself a product of two other functions. H of x here is defined as being equal to f of x times g of x. And so, of course, we know how the product rule works. If we differentiate, we have h prime of x equals f of x times g prime of x plus g of x times f prime of x. So we're essentially taking this and rearranging it and using it to come up with an integral for certain specific cases. So first things we're going to do is just actually take the integral of both sides, which we certainly are allowed to do. So we have h prime of x dx equals, and on the right-hand side, inside the integral sign, we have the product rule dx, and then we can rearrange it algebraically, and we end up with h of x equals f of x times g of x, which we already assumed, and that is going to give us the integral of f of x g prime of x plus g of x f prime of x dx. Now, ultimately, now we've got all this algebra going on here. Right here, this is what we're looking for. So, and by the way, in many textbooks, I'm sure you've noticed this already, some books will use f of x and g of x to represent two different functions. And then there'll be the equivalent derivatives f prime of x and g prime of x. Sometimes it's easier to use a simpler notation. A lot of books use instead u and v, and then f prime of x becomes u prime or du dx, and then v becomes v prime, which is the same thing as dv dx. So this really scary looking definition, if we use this approach, can be reduced to what you're seeing right here. And you can see it doesn't look nearly as terrifying as this one, in my opinion. I think it'll be infinitely easier for you to remember this one rather than this one. Okay, so remember, u is now the f of x, v is g of x, so that f prime of x dx is du, and g prime of x dx is dv. So if you run across a situation like this, you're taking the integral of u dv, then you can use this technique of integration by parts. Now, like with some of the other techniques that we've used, such as u substitution, if you do this incorrectly, if you choose the wrong values to substitute, you'll find that you end up with a bigger mess than you started out with. And that's how you know you're going down the wrong path. So if things look simpler, sorry about that, then you know you're probably heading in the right direction. All right, so why don't we start with a simple example. Now, first things first, if you notice, you've got a product. Okay, now you also notice, though, that x is not the derivative of sine of x, and sine of x is not the derivative of x. Okay, so you're not using u substitution. What do we do? All right, so here's what we have to decide. What should we call u and what should we call dv in this integral? And again, it's not the end of the world if you get it wrong the first time. You can, because like I said, you'll notice it immediately that you're heading in the wrong direction. You're making it a lot more complicated. And that's how you know to go back and try something different. So here, what you would have is this. All right, so why don't we try this? Let's have u be sine of x. and then dv is sine x dx. Now, here's where we have to be careful. With u substitution, we have u and we have du dx. Here we have u and dv, which means that these two aren't necessarily related to each other. Instead, what you have to worry about is accounting for everything that's under that integral sign. So if u is x, whatever's left over has to be dv. Okay, now let's see if we've successfully chosen the right approach. If you look at this formula, what we're still missing then is we have u, we don't have v though. Okay, so dv is sine x dx. What does that suggest about v? Aha. So in other words, the dv gives us a clue as to what v is. V is simply the integral of dv. So then all we have to do is go back to our tables or our charts, or if we happen to remember them, and we'll see that the integral of sine x is the negative cosine of x. So right there. Now we also need, so far we already have definitions for u and v. Uh-oh, what about du? Well, this one happens to be a very simple one. If u is x, then du is dx. Okay, so guess what? We have everything we need now because, oh, and by the way, you notice how with this one we're using indefinite integral. We of course, as usual, only need one constant. So let's gather up all the information we have. First of all, let's remind ourselves what the rule looks like. So we can see it all in one place. And just a quick reminder, u is x, u is simply dx. By the way, here's one thing you got to watch out for when you're writing this definition. U's and v's can be start to look like each other if you're not really careful. I'm going to have to discipline myself to make sure that I don't get too sloppy here. V is, as we've just seen, by taking the integral negative cosine x, and we're not going to need to include the constant in that. We're just going to save it for the end. So dv, we've already chosen to be sine x dx. All right, let me do this out of the way. That implies that this is negative cosine x. Okay, so then now it's just substitution, right? And again, you'll see that if it appears that we're simplifying it, that means we must be doing it correctly. So u is here. There's v. Now here, don't forget we're subtracting. V again is negative cosine x, and du is dx. So out here we have negative x cosine x, and we integrate cosine x. And again, if you want to look this up in the book or in a table or something, you'll recall that the integral of cosine x is sine x. And so this is our final result. And of course, if you want to, you can always feel free to double check. You can multiply, or sorry, take the derivative of this expression, and it will bring you back here. Okay, given that the c drops out when we differentiate it. Oh, it looks like I forgot. I put this in here, a very helpful reminder. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Integral, and you can see why this has to be written this way. Oh, by the way, don't forget, the book has these. Let me just open it up for you. I don't remember exactly where, but the book has an enormous table. I think it's in the appendix. There should be a separate chapter at the end or a separate appendix. And all it is, yeah, there it is. So somewhere down here, it has the trig functions. There it is. Okay. So the integral of sine x, or in this case, it's u, but it's sine x dx is negative cosine x. Integral of cosine x is sine x plus c. Okay. Then we also, somewhere along the way, had the derivatives of the sine trig functions in an earlier chapter. I don't think there's a separate table in this book for differentiation functions, just because it's not really needed in the same way because you don't have quite so many possibilities to choose from. Okay. Where is it? Oh, it's probably 5. All right, let's see. Wow. Maybe not. Um, all right. But I know somewhere along the way we did that. I'm sure it's in the slides, but let's see if we can find a table on the internet. Well, all right, here's one. Um, and so you can see the derivative of sine x is cosine x, and derivative of cosine x is negative sine x. Okay, they're all here, and this is good because this one has all of them listed together in one place. So, I find it personally to be very helpful to have tables like this that I can just go flip through it and find what I need very quickly and easily. Otherwise, it's easy to lose track of what you're doing. But anyway, so this is our final result. We're done here. So again, how did you know that this is integration by parts? Because like I said, unlike cases that we've seen before, if you remember, if you had something like this, oh, let's say it's something like this. Then in this case, you could call this, use u substitution, and you'd have u is 3x squared plus x. And then du dx is simply 3x plus 1. And so du would be 3x plus 1 dx. And so you'd see you'd have this nice form here, u du. It would ultimately end up with 3x squared plus x squared over 2. And so this is what we called u substitution, but it requires us to have something in the form of u, some function of u, and du. Here we don't have that. Okay, so as you can see, it's pretty clear that this is not going to be a case for substitution or u substitution. So that's why we have to try something else. And that something else might very well be integration by parts. Now, if you work with integration by parts and you still aren't getting anywhere, like if this was sine squared of x, for example, you might find that this is absolutely not the appropriate technique anyway, and you have to move on to something else. But as long as it works, if you try this and it works, you know you must have done the correct thing. And especially if you can double check it and make sure that your result equals the original integral. All right. So by the way, later on, I have a bunch of practice problems that I want to present as soon as we're done with chapter 8. Oh my God, look at this one. Now, this one, now, by the way, sometimes an integral can be done with more than one technique. It's not the case that each one has one technique and that's it. In math, typically we have multiple ways of getting to the same answer, which is a good thing. And So you may decide that, you try one approach and it works, and you'll say, well, how come the answer in the book shows this approach? Well, often there's multiple ways of getting to the same result. So here, what we're going to do is try integration by parts, even if there are other possibilities. And so let's try this. Let's let u be the x and dv be the rest of it, whatever's left over, e to the 2x dx. So that means this is the tricky. Now, this looks very much like e to the u du. And it is, but so if u is 2x though, see what the problem here is that we need 2 dx. Whoops, sorry. This should be 2, and then du is 2 dx. We don't have that, but we remember from a previous chapter that we can supply it because all that we're missing is a constant. So we rewrite this as and so we haven't changed anything. And now we end up with 1/2 e to the u du, which is 1/2 e to the u plus c, 1/2 e to the 2x plus c. So it means here v is simply 1/2 e to the 2x. All right, don't worry about the constant. We'll put that in at the end. All right. And also, I mean, if you notice here, this is our old friend, the method of substitution or u substitution. So even within a problem that is meant to be solved with integration by parts, in order to find v, since you're taking an integral, you might potentially be called on to use any other technique that you've already learned. So the same problem can involve multiple techniques. And that's exactly what happened here. Okay. So now this is our final result. U is x, du is dx, dv is e to the 2x dx, and finally v, based on our integration with the method of substitution, is 1/2 e to the 2x. Well, now it's just a matter of substitution. All right, so I'm going to copy these, if it will let me, onto the next slide. So you don't have to keep scrolling back and forth. Yeah, this one was created with math types, so it behaves a little differently. All right, and so here's the integration by parts formula, okay, which we first introduced right here. So we look at it and say, we're suspicious that this might be a job for integration by parts. How would that work? All right, so let's try the substitutions. U is x. Then we need the v. Then we need to subtract off the integral of v again. Du in this case is very simply dx. Now, if you notice, we have two more terms. And the first one's fine. It's all set. I just rearranged, the constant got moved to the outside. This one now requires us to use integration with u substitution again, which is not a problem because we're very familiar with it. So here's what we'll do. We need the 2 dx to make this work. So we'll multiply and divide. This becomes -1/4 integral e to the u du. And here the u is 2x. Okay, so that gets plugged in over here. And so ultimately we end up with 1/2 x e to the 2x Let's go back and double check that. That's right. And then here we replace this part with negative a quarter e to the 2x. And then we finally sneak in the c there at the end. Oh boy. Okay. So it does take a lot of practice, but you'll get good at it very quickly. And again, you'll see this again in Calc 2. This is pretty much where you'll start. If you're taking it in the fall, in September, they'll probably review with you and then dive right into this chapter about integration. Because you have a lot of ground to cover, and they have to assume that you learned all this stuff in Calc 1. So anyway, so now of course, we might be asked to do integration by parts with definite integrals. And so we just have to be careful because we have to evaluate everything between A and B, not just the integral on the right, but also UV itself. So you notice how we have the limits of integration, just to remind ourselves that we're actually integrating over this interval. And so we have to evaluate everything we come up with in between A and B. Okay, now, like I said, that was really just meant to be a very brief introduction to the subject matter. At the end, I've written up a bunch of practice problems, but I want to save them until this chapter is over. So I'll tell you what. Ooh, I really hate to make up problems right on the spot because it's easy to have problems with it. I'll tell you what we'll do. Let's just go grab this one and see what would have happened. Let's say here's the starting point. That's her initial integral. And we did a lot of work to discover this integral is this. So suppose we had instead something like this. So we would have had the first term is evaluated. We've already done with the first term, so we'll evaluate that between 0 and 1. And then we would have integrated this term, 0 to 1. But we already know that that's equal to this. So we'll have 1/2 x e to the 2x minus 1/4 e to the 2x evaluated from 0 to 1. And now we just make the substitutions. So there's nothing actually different here. Okay, so in other words, you would have this is f of 1. This is f of 0. So what do we have? 1/2 e squared minus 1/4 e squared. This is all just 0. Oh, actually, no, it's not. Sorry. The first term is 0. The second term is 1/4. E to the 0 power is just 1. So you ultimately ended up with 1/2 e squared minus 1/4 e squared plus 1/4. And if you want to consolidate these two terms, you'll end up with negative 1/4 e squared plus 1/4. And that would be the definite integral That would be the area under the curve between 0 and 1 for this function, if you need that information. Okay, so we'll come back to this again when we start working on the word problems or the extra problems, which we'll do at the end of this chapter. In the meantime, why don't we switch over our attention to the trig integrals? Trig integrals are kind of interesting because what you're looking for is a certain form that you can recognize. And so, for example, what we're going to be doing is integrating powers of sine x and cosine x, tangent and secant x, and then we're going to use a bunch of identities. There's so many identities with trig functions that'll help us simplify our results. Now, we did briefly mention this once before. In fact, I put some of them in the appendix to this section. Just as a quick review, well, for one thing, it turns out that you can actually solve for the sine or cosine of any angle by using what's called a unit circle. Now, this is a circle whose radius is 1 and who's centered at the origin. And so if we define a right triangle here, you'll notice something interesting. Based on angle t, because this is a unit circle, the radius is 1. That means the hypotenuse of the circle is 1. But because of the way sine and cosine are defined, it turns out that the xy coordinates of this point are the cosine and the sine. Okay, so remember the sine is opposite over hypotenuse. And so from the perspective of t, the opposite is here, and the h is here. And since h is 1, then the sine is just equal to the opposite side, or the height of this segment, which touches the curve at point y, which means that is our sine. Okay, so in other words, this is the sine of t right here. And that y coordinate you see here is the sine for that reason. The sine is the opposite, which means the height of that triangle, which in turn equals the y coordinate of that point. And then since the cosine is the adjacent over the hypotenuse, and again, h is equal to 1, that means the cosine equals a, and that would be this side. So here's our xy coordinates. So if you were to draw this triangle, you could calculate the sine and cosine of any angle we need. And the reason why that's so important is because if we know the sine and cosine, we can calculate all the others ourselves. Because if you recall, the sine of theta over the cosine theta is the tangent. Actually, let me move that. What about the others? Well, the cotangent is the inverse of the tangent, which means we can derive it as simply the cosine over the sine. What about the secant? That's the inverse of the cosine. And what about the cosecant? That's simply the inverse of the sine. So in principle, if you know the sine and cosine, if you derive them from this unit circle, then the others all just fall right into place. Now, if you've ever looked at your calculator and said, how come it only shows me the sine, cosine, and tangent? That's because the other three are simply functions of the sine, cosine, and tangent. In fact, even the tangent is not absolutely necessary. But they figure you want all three of them, but they're not going to give you the rest because you don't need them. Anyway, but then you also remember your old friend, the Pythagorean theorem. And that just means a squared plus b squared equals c squared, which implies that sine squared t plus cosine squared t equals 1. since the sum of the squared sides equals the square of the hypotenuse. And we know that the hypotenuse is equal to 1. That is known as the Pythagorean identity. Now, that is the starting point for many other identities that could potentially come in handy. For example, let's take a look at this. What if I divide both sides of this equation by cosine squared t? I can certainly do that without affecting anything. Look what happens. Uh, Suddenly I have a 1, I have a tangent squared, that is, and I have 1 over a cosine. It becomes the secant. Okay. So in other words, if 1 over cosine theta is the secant, that implies that 1 over cosine squared theta must be the secant squared. So this is one of our identities that you never know when it might come in handy. I'm not sure if this book has a list of these trig. I think it must. There's got to be somewhere in here where it's got trig tables. Maybe not. I don't know. It's hard to tell. Let's look. Maybe not. I'm a little surprised to see that. Maybe they sneaked it into the different chapters. But if you go to the internet, I'm sure you could find a table. If you just type trig identities, there's got to be one out there somewhere. Yeah. Ooh, this one's nice. Look at that. Geeks for geeks. How do you like that? Um, that's a pretty comprehensive list. Oh my God. And what I love about it is they're going to go ahead and prove them all to you. Be amazing. So, but yes, if you had a copy of this chart with you, you'd be in pretty good shape. So let's leave that there for the time being. Some of these other ones, yeah, even odd identities, for example, because some of these are odd functions and some are even, you get these results. And then you have these formulas for half angles, as they're called, and there's all kinds of them. So these are some of the ones that might come in handy. There's also double angle formulas. There's all kinds of formulas. Anyway, there's another one. Now, if we take the same starting point, the Pythagorean identity, and divide both sides by the sine squared of t, oh, now this time, look what it reduces to. Cotangent squared plus 1 equals cosecant squared of t. So, you'll use this only when it's really helpful. You don't just use these for the fun of it. But you never know when you might have a horribly complicated formula. In fact, on the midterm, there was one that surprisingly enough reduced to 0, if I remember correctly, because of these identities. Anyway, so that I put that in the back in case you need it. So let's get back to this now. So here's what are the so-called double angle formulas? Or this is going to give us one of the double angle formulas. Now, unfortunately, it doesn't appear that this chart that I just found has it. But it turns out that the sine of x plus y can be rewritten as the sine of x times the cosine of y plus the cosine of x times the sine of y. All right. Now, what if x and y are both equal to the same angle, theta? Then the sine of x plus y could be rewritten as sine theta plus theta, sine 2 theta, which we were just told equals this. And now we simply replace the x's and y's with thetas. And so we have sine theta, cosine theta plus cosine theta, sine theta, which is the same thing as 2 sine theta cosine theta. So the double angle formula simply says that that's one of the double angle formulas. Now, what about cosines? Now, sines, let's get this together so we can remind ourselves and see how they're different. All right, so this time it's cosine xy minus sine x sine y. So we can use this to derive a double angle formula for cosines by following basically the same approach. X equals y equals theta. So ultimately we end up with this. Right. Then we also know just from the original Pythagorean identity how to rearrange this algebraically and solve for cosine squared theta and sine squared theta. Now, why are we doing this? Because we're going to plug them into these double angle formulas. And here's what we end up with. So the cosine of 2 theta, as we saw before, is cosine squared theta minus sine squared theta. But remember, too, um, cosine squared theta from the Pythagorean identity is 1 minus sine squared theta. Okay, and so you end up with this. So this is another version of the double angle formula for cosine. And again, you never know when it might come in handy. And then doing the same exact thing, we end up with this. Make the substitutions. This is the equivalent of sine squared of theta from the Pythagorean identity. And this is what we ultimately end up with. So those are two of our double angle formulas. You notice that we end up with two different results here, but they are obviously equivalent to each other. Now for tangents, and you notice there's so many of these identities. This is our starting point. Once again, we have the same strategy. We let x equals y equals theta, and we end up seeing what happens. This is going to become tangent to theta. And so we end up with 2 tangent theta over 1 minus tangent theta squared. So I very helpfully put a bunch of these together in case you need them. These are the so-called sum and difference formulas. So if you notice, we only were looking at the sums earlier. Okay, sine x plus y, cosine x plus y. What happens if we're subtracting? Does it make any difference? Yes, it does. But you can see it's just the sign that changes. So those two are only different by the sign. And down here, it's the same thing. It's the only thing that's different is the sign. So we call those the sum and difference formulas. Same thing with this tangent. We only showed the one with the sum, but the difference has its own version. And then these are some of the double angle formulas. Again, you never know when you might need them. Now, nobody expects you to memorize them, but you should at least have them in a nice little chart in front of you when you're doing your assignments. Now, we're going to introduce these so-called reduction formulas, whose what they're basically doing is taking our double angle formulas and explicitly using them for the purpose of simplifying a very complicated trig expression. So, sine squared of theta can be rewritten in this form. Now, let's see if that chart has this. So you see what they've done. They're writing it like this. This is the first of the so-called half-angle formulas. They wrote it as sine theta is plus or minus the square root of 1 minus cosine theta over 2. But of course, it means the same thing. So these are the so-called half-angle formulas. Um, and oh, I see what they've done. I didn't even notice that. Um, they have replaced theta with theta over 2. You see what? Oh, okay. I kind of went right past that. Um, it's kind of confusing. What they would say is saying here is that if you have sine squared of theta equals 1 minus cosine 2 theta over 2, that implies this. Okay. And then you can rewrite that as yeah. So in other words, that's how the theta for sine is now 1/2, and the cosine instead of being 2 theta, it's just theta. Again, it all means the same thing. And also, I just realized I left the square here. That was not correct. Okay, now we're good. Now we're good. Okay. So yeah, just keep an eye on this part. So there's more than one way of writing this, but they do it that way. I think just to make it clear, this is why they call it a half angle formula because the way they've written it, it's theta over 2, the sine of theta over 2. Although it means the same thing as what we have down here. Then based on the same exact logic, we end up with this. And of course, if you notice in the table, this is how they've written it. Cosine theta over 2 is plus or minus radical 1 plus cosine theta over 2. For the tangent, remember tangent theta is sine over cosine theta. If we square it, everything gets squared in the expression. And then if we replace the two double angle formulas or half angle formulas, sorry, that we just created, this is the final result. Okay, that's just algebra. So now these are referred to as the reduction formulas, or, well, all right. I mean, it means the same thing. You can see here they're calling them half angle formulas. Here in our book, they're not dividing it by 2, so they're just calling it the reduction formulas. It's the same thing. And we're also not taking square roots of both sides. So obviously these formulas and these are the same thing. Now, finally, we get to discuss what we were interested in here, which is to say the derivatives and integrals of sines and cosines and tangents and all the rest of them. But we did need to come back here and introduce a lot of these formulas because we were going to need them in several cases to simplify our results to something more manageable. Okay, so with trig functions, if you're stuck, sometimes the trick is not to find another technique, but to see if there's some way you can rewrite your expression in terms of these special double or half angle formulas, or even just simply using the Pythagorean theorem. Well, all right then, let's take a look at some of these. Here we go. So we got the sine and cosine raised to the j power. So obviously if j is 2, that's squared. J is 3, it's cubed. What do we do now? Well, we can potentially use substitution, but we may have to first use some algebraic identities to do this. Here we go. Now, here we got to have a bunch of cases. You notice what is written here. We have cosine to the j power x sine x dx. If you have an integral rather that falls into this format, then you can use what we're about to do. So we have cosine cubed of x sine of x dx. What should we do? All right, well, now we're going to try u substitution. This is not integration by parts anymore. This is straight ahead u substitution, but maybe we can pull it off, maybe we can't. So let's try this. U is the cosine, which means here we have, and if it is, then the derivative, remember, we saw a little while ago, is the negative sine of x. But we don't have that. We need to supply that ourselves. All right, now we're looking pretty good. Okay. So in a way, it's not very much different than what we've done before. It's just that, you have to recognize this part. Knowing these simple trig derivatives is hugely helpful because otherwise you might not have realized that you can simply do this with integration with u substitution. Now, look how, in this case, though, look what happened. We've got cosine of the j of x, but we also have sine of the k of x. So what we're about to do only works when k is an odd power. Now, that's what we just had a minute ago, because there's an implicit 1 here. Okay, so what we're about to do could have been used in this case. We're going to take the Pythagorean identity and rewrite it. So the sine squared of x is going to be rewritten as 1 minus the cosine squared of x. How does that help us? Okay. What do we do with this? Let's rewrite. Sine squared of x as 1 minus cosine squared of x. Ooh, now what's that going to get us? Good question. So now we would like to know if there's a way we can use u substitution. Of course, that's our favorite technique in the world. So let's see what we can do with this. So let's try this. U will be cosine of x. If it is, then du would have to be negative sine x dx. Now, one thing we can do is rearrange this a little bit. You notice how we don't have this negative for our du. We're going to supply it right here. Wow, what do we do now? Multiply that out. Oh my God, there's so much to multiply. What you've got is, remember, we chose u to be cosine x. Du is negative sine x dx. So if you make some substitutions here, what do you actually have? U squared, 1 minus u squared. And then all of this is just du. And don't forget the negative sign. But what we can do now is multiply this out. So we'll have negative u squared minus u to the fourth, and each of those terms can now be solved with the power rule, very simply. So we end up with negative. We have u cubed over 3 minus u to the fifth over 5. And then we just simply replace u with cosine of x, and this is our final result. Wow. So what exactly gave away what we were supposed to do? Well, it's the odd power for the sine. As long as you use the Pythagorean theorem and some algebra, then you can use u substitution, and you'll end up with your result. Wow, this is pretty deep. Now, if you notice, these two cases involve both the cosine and the sine. What about cases where we just have one or the other? For example, what if we need something like this? Well, one possibility is to use one of these so-called reduction formulas. And if you notice, we did not rewrite it as a half-angle formula. We left it the way it is. We had this a few minutes ago. 1 minus cosine 2 theta over 2. It was up here. Here it is. All right. So what we're going to do is this. Just make the substitution. And this is what we end up with. Now you can simplify it a little. You move the 1/2 outside, and then you can break this up into two integrals. You'll have 1/2 of integral of dx minus 1/2 integral cosine 2x. So this one is easy. How about this one? Well, this is just straight ahead u substitution. Oh, actually, no, it's not, because we don't have what we need. It means we may be using another double angle formula. No, we don't need a double angle formula. We can use u substitution because we're going to treat this as the u. But we do need to supply a constant. Actually, we could have probably used a double angle formula, but this is probably more straightforward. So why don't we follow along with this? So 1/2 cosine 2x dx. We need to supply the 2, which means we need this 1/2 here. And end up with 1/4 cosine u du. And remember, the integral of cosine u is sine u. And therefore, we have 1/4 sine u or 1/4 sine x. So the first integral was this one. We combine that with the results of our second integral, and our final result is the sum of these two, plus the c. Never forget the c. Okay, so remember, we took this one and subtract this one. So we ultimately end up with a half of x minus 1/4 sine x 2x, or sine 2x plus c. All right. So now what's coming up next, we've got a couple more of these with different values of the exponents. And then we'll eventually get to secants and tangents. And we'll look at several cases. But we don't have to get too carried away. A few examples will do. And all right, so actually I think we can stop right here for this session. When we come back, we'll wrap it up with these other cases. And then in the next section of this chapter, we're going to be considering, oh, now this is a completely different technique. It is meant for very different cases where you have something like this. We have a messy function in the denominator, some kind of polynomial, and we can often take it and break it up into much simpler pieces following this very special technique, partial fraction decomposition. But we'll have to say that for later. That's 8C. Right now we're halfway through 8B. So we'll probably in our next session, we'll wrap up 8B and then do 8C, and then we'll be done. And what will remain is the problems that I want to work on. And then we'll be in pretty good shape. Okay, in other words, the course is winding down very quickly. We're getting very close to the end. And by the way, I must say people did really well in the midterm, which is good. The final should be of a similar difficulty level. There might just be more material on it. So I think you'll all be fine. So, all right, anyway, don't forget the chapter 5 problems are not actually due until the 21st because of the length of them and the fact that we're getting so close to the end. In fact, our official last day is July 29th, which is a week from Monday. Isn't that right? No, sorry, 2 weeks from Monday. It's not quite that late, but that's still late enough because we have to finish up we have another assignment and we have to review, and then you'll have to do the final exam. Okay, so I'll see you all next time.